Hello, ladies and gentlemen, and welcome to today's broadcast on recent developments in ion mobility, mass spectrometry, enabling structural and isomeric separation for large and small molecules by Dr. John Fjeldsted, the distinguished scientist and senior director for ion mobility and intellectual property at Agilent. And I'm Susie Valdez of LabRoots, and I'll be your moderator for today's event. Before we begin, I want to encourage you to engage with us. You can submit as many questions as you want at any time you want during the presentation. Simply type them into the Ask a Question box on the left and click Send. We'll answer as many questions as we have time for at the end of the presentation. If you have any trouble seeing or hearing this presentation, just click on that support tab at the top right or use that Ask a Question box on the left. Join me now in please welcoming Dr. Fjeldsted. You may now begin your presentation. Welcome, sir.
My name is John Fjeldsted. I'm with Agilent Technologies in Santa Clara, California. It's a pleasure today to join you as part of the Solving the Unsolved in Mass Spec series. I have two principal topics that I'd like to cover today. The first is to do with resolving power increase enhancements in ion mobility mass spectrometry. That's largely associated with small molecule analysis. And the other happens to do with collision-induced unfolding of proteins, large molecule analysis application. When we look at the history of ion mobility, we realize it goes back over 100 years, but it's really only been the last 15 years that ion mobility has been effectively coupled to mass spectrometry for analytical analysis. Today, I'd like to focus on these numbers 1, 2, 3, and 4, which are various mechanisms for which ion mobility resolving power can be enhanced. Let's begin with trapped ion mobility mass spectrometry. This is offered by Bruker and was introduced in 2016. The analyzer is composed of two sections, one a section that accumulates and a second section that does the actual ion mobility separation. And this can be achieved at various rates, release rates of the ions through that analyzer section and the exit funnel. The resolving power is increased as that scan speed is decreased by the 1/4 power. And let's look at an example of how that actually works out. You can see on the left-hand side these two hydroxyflavanones that are separated nicely at a resolving power of 40. Now, this analysis was done full spectral range, so nearly 200 square angstroms, and acquired at 11 frames per second. On the right-hand side is the exact same sample, and in this case, to increase the resolving power to about 120, the scan rate of releasing ions through that separation had to be dramatically reduced. And so to do that, to accomplish that, the range was reduced to 16 square angstroms. That's the width of what you actually see in the spectrum. And the acquisition rate was reduced to 2.5 per second. So this results in a total reduction of about 50-fold in scan speed. And the square root of 50 gives you about a factor of 3. So that's consistent with the results that you see there. When we consider what that means for the actual analytical application, we start at a resolving power, a base resolving power of about 40, and that gives us essentially a full range analysis over mass and collision cross-section. When we want to increase the resolving power, in this case to 120, then that reduction in the actual range that can be monitored to accommodate that slower speed, as well as the acquisition rate, is reduced by about a factor of 4 as well. Then this turns the analysis essentially into a target analysis to be able to accomplish that higher performance. Okay, it also comes with a reduction in sensitivity and in dynamic range as a result of the reduced frame rates. With waters and their traveling wave ion mobility system, in the introduction of a cyclic device, which you can see in the center of the screen here, which allows incoming ions to then be pushed into a ring, and that ring can accommodate multiple cycles, allows each cycle giving an effective length increase and increase in resolving power. When we look at how that deploys then analytically, here's a couple of analytes that they've published on where we have a single pass achieving a resolving power of nearly 80. And then once 16 passes are accomplished, you can see there a resolving power of over 300. So this is really quite impressive. Albeit though, each time we increase the number of passes, the actual CCS window that can be put into play also commensurately decreases. So once again, turning the analysis into a target analysis with that increase in resolving power. So if we look at that, once again, a first pass, a second pass, each time reducing the actual zoom window, and then also increasing the analysis time. I'd like to now move to resolving power increases that are possible with Agilent time-of-flight mass spectrometry. The instrument on the left is the drift tube ion mobility system that was introduced in 2014-15. And the one on the right is a new system that we're working together with Mobile Ion. You can see the logo on the front, which is a developing technology that came from Pacific Northwest National Labs, Dick Smith's lab there, and makes advantage of an increased path length through the SLIM technology. Okay, let's under the hood we see the drift tube on the left. That's the standard 6560 instrument, and on the right you can see the serpentine path of the structures for lossless ion manipulation, or the acronym we use is SLIM. All right, and needless to say, with the increased path length, we're going to expect a higher resolving power. The instrument looks like this. It actually has a traveling wave that's implemented on circuit boards. These are planar circuit boards. You see that here on the right. And what we've done is we've zoomed in on a portion of that. The circuit boards actually exist in a layer. There's two, an upper and lower, and the fields that are generated between them are allowed for the propagation of the traveling wave, and also the confinement lines, or the red lines that have RF that hold the ions in play there. Now, with that, you can imagine we're going to take that 13 meters, and now we're going to sample it with a QTOP mass spectrometer. This is nice because it's a modular design that allows for the SLIM separation front end to be coupled to an Agilent QTOP, an existing system. Now, we'll look at this. The time-of-flight analyzer is the back end of the QTOP, and as you well know, the acquisition rate of time-of-flights are very fast. In the 1700 mass range mode, that's 8,000 transients per second. So let's let those ions fly through the SLIM device, and as you see, the acquisition of TOF transients captures each of those analytes passing through that have been separated by ion mobility. And when we transfer that to collision cross-section calibration, then we get a resolving power of about 250 to 300. Okay. Now let's actually look at this here. We realize there's a time advantage versus condensed phase separation. So let's take a look at this in more detail. That 13-meter SLIM separation is accomplished in about 1.5 seconds, and achieves a resolving power of about 250. So you see the square plotted in the middle of the frame there. We can also redirect those ions that are about to exit and go to the QTOF and repass them through the SLIM device for a second or third time. And this increases then the resolving power with each pass. Now let's compare that, as I mentioned, to say UPLC, which achieves similar resolving powers, albeit at a longer time scale. So the opportunity that presents itself is, can we take some traditional UPLC separations and remap those into a SLIM separation, achieving similar peak capacity, but in a substantially reduced time scale. The reason why we're able to do this with SLIM is because, if nothing else, and what we'll show you to is just single pass separations, is that we're able to collect all of the ions. It's not just a targeted resolution enhancement approach. So how do we do an analysis like that? Well, we can take the analyte of question and we can introduce it in a liquid stream to the atmospheric pressure ion source, and we can do it as a flow injection analysis plug. That's what I'm depicting here, or we can do it as an LCMS experiment. But I'm going to show a few FIA experiments, so I wanted to give a little bit of background on that first. So we're collecting frames. These are the two-dimensional ion mobility by mass separations. And that takes about 1.5 seconds, so we can get 20 frames in 30 seconds in this example. And we can sum those frames together. Now that's going to increase sensitivity and dynamic range. And now we have essentially a two-dimensional separation, one by mobility and one by mass. And if we wish, we can remap that mobility and plot it as retention time. That way we can use existing QTOP data analysis packages and existing workflows through any informatics that a person would want to do in that regard. So let's take some examples of that. The first one I'd like to do is, yes, it is a large molecule, and we're going to give a little bit of an example of that intact, but we're also going to look at some digestions as well. So first, considering some of the challenges with monoclonal antibodies and looking at their stability, then deamidation and isomerization, those are two of the toughest ones because the mass shifts are rather small. Let's take a look at the NIST standard that's referred to here on the screen. And on the left-hand side, the first example is just doing what we mentioned there, doing an FIA analysis, summing 2 minutes worth of frame transients that are acquired, summing those and then remapping them into a standard retention time mass spectral context, and then analyzing those using standard deconvolution, a multi-charge state deconvolution, and looking at then the glycosylation sites by mass here on that intact protein. This can also be done with the subunit, and in this case, the subunit, instead of doing an FIA analysis, we actually did a short LCMS analysis. You can see the results here comparing straight LCMS without ion mobility together with the addition of ion mobility. Now, let's take a look at what that ion mobility can do, and let's look at it at this FC region for just a minute. You can see some of the raw data on the left here in a two-dimensional plot. What we're going to do is now take and pull a spectrum off of that, look at the arrival time here in milliseconds, and we're going to look at this at the FC region at two different time points during the reduction, one at 20 minutes and one at 60 minutes. And you can notice the black trace here at 20 minutes. The disulfide bonds are still intact there, have not been broken and reduced. And then we can see the arrival time distribution is shorter than after 60 minutes of reduction when the bonds break. And of course, now you've got an elongation and opening of that FC region. It gives goes from a compact format structure to a more open. We can also, as I mentioned, do a digest here. And in this case, we've done a short LCMS separation, just 5 minutes. And during that, we've been able, using peptide mass fingerprinting, we get nearly a 99% coverage. When we move over and want to see the value of the ion mobility, let's look at the right-hand side here. So if we look at this here, we've got asparagine, the N here, and the native form, but we also notice that some of that is converting here to aspartic and isoaspartic acid. We can actually see both forms, both conversions here, because each of those are actually drift time resolved, as you can see in these stacked plots. We go to this second peptide here, okay, in this case, 2 asparagines, and we're seeing actually just a single conversion at this point, that we can see that separation and drift time. This is a big help because otherwise, just that single shift in one mass value, or 2 of them shifting each by 1, would largely overlap the isomeric, the isotopic patterns that we have from the native form. And generally, that's achieved a better separation by chromatographic separation that allows for that distinction. And here we're able to achieve that in just a 5-minute time scale because we're not relying on the chromatographic separation. Rather, we're augmenting that with the mobility separation. Let's look at now some release glycans. Okay, this is from RNase B and from Fedouin, and we can see here that this analysis for these release glycans is generally done over 180 minutes, and you can see some extracted ion chromatograms from various glycan families here over that separation. We've done a flow injection analysis over 2 minutes, and now we're letting the drift time or the arrival time distribution of the SLIM actually be mapped here to the x-axis as this is the case in a chromatographic separation, and looking at the various glycan families that separate here very nicely. The thing that is the interesting contrast is if we compare the 2-minute infusion to the 180-minute separation, this is a 90-fold increase in throughput. And on the right-hand side, you can see some of the the comparisons of the separations that were done chromatographically or by drift to show that we're getting similar results, and we're able to quantitate on these in a very similar fashion. And if we look at these relative responses here across these families in the bars, we can see that that matches very nicely to the spectral display that we have here from the SLIM. It can also be applied to complex systems like lipids. So here, with the various isomeric forms of lipids, we've got cis-trans separations that are now possible. We have SN positional isomers that are separated, as you can see in the middle, as well as moving the double bond along the chains. We can separate those double bond positions. That's very exciting. So to summarize, here's where we stand with the SLIM technology. Now let's add on the drift tube technology, and we see that with a shorter drift length compared to the 13-meter path, we also get a lower resolving power. Typical resolving power between 50 and 55 for singly charged analyte. But we also notice that it happens at a rather short time scale. This is down at around 50 milliseconds. Okay. So with that, that measurement system is very similar to what we just saw with the SLIM. We have a drift separation. Now this is happening, as I mentioned, at 50 milliseconds. That's 20 times a second. And the TOF spectra are being acquired in the same way. And we get a resolving power between 50 and 60. Well, you may ask yourself, where's the high resolution in that? Well, that comes by some new methodologies that we've been applying here in the last year. Let's take a look at how we achieve that. First, we realized that ion mobility, and in particular drift tube ion mobility, can be operated in a novel two principal ways. One is a trap and release, as you see here, a single pulse for the standard separation time of, say, 50 or 60 milliseconds. But we can also do a multiplex mode where we have multiple traps and releases all in a single analysis period, all within a single frame. All right. And that gives a great increase in sensitivity, duty cycle, and we can also use that to benefit resolving power. Let's see how we do that. First, let's make that measurement again. This is just now looking at that multiplexing, where we realize with that pseudorandom sequence, we continue to drive multiple accumulations and releases in each measurement cycle. And once again, we're acquiring that at about 8,000 TOF transients per second to be able to capture that. To enable to use this data, we have to go through a demultiplexing step, and we take that pseudorandom sequence, that coding, we know exactly when the ions were released, and now we can apply that. We take the open gates and the closed gates, and we transform those to ones and minus ones, and we overlay that on the raw data using an autocorrelation to be able to then grab each of those multiple pulses across the frame, summing them up based on that correlation, and that gives a sensitivity increase. Now, we can take it a step further if we want to do resolution enhancement by actually knowing what each ion characteristics are in terms of passing through the drift tube. Now we trap them and we release them, and during that, we get a diffusion broadening that results in a resolving power of about 50, as I mentioned before. If we take that what we refer to as an instrument function, which is really just the actual envelope of the peak width of the ion mobility separation in a fundamental sense, and we replace the ones and minus ones, or with that instrument function, we can now use that to do a simultaneous deconvolution as we're doing the autocorrelation function. And that results then through that deconvolution in, as you see here depicted as a smaller point, which is trying to give giving the indication of a higher resolving power. So we realized that those points were starting to get so narrow that the basic TOF acquisition rate of 8,000 left the mobility separation peaks undersampled. So in a post-processing sense, now before we do the deconvolution, we actually interpolate additional TOF spectra to up to 24,000 now per second. All right. And with that fundamental higher sampling rate, we're able to produce a higher resolution when we pass the inference function over and apply the deconvolution algorithm. Okay. Let's see what that looks like with some real data. Here you can see on the left-hand side some PE lipids, and you can see the isotopic envelope, and you can see that there are multiple pulses all stacked over the, in this case, 60 millisecond per frame separation time. Now, using that autocorrelation routine and the deconvolution, you can see that function. When that passes over, we're able to get that resolution enhancement. And now we're showing the output data file on the right-hand side of this slide. Notice the increased resolving power. Also notice that those peaks are taller. The actual area or ion current has not been lost. And so we actually get higher detectability from that as well. Now, this is accomplished in 2 programs. I mentioned the first program achieves a drift interpolation. This is done through the PNL preprocessor. This is work that we continue to do with the Pacific Northwest National Labs and development of these preprocessing routines. And the second is the autocorrelation and demultiplexing and deconvolution that happens through the through the high resolution demux tool, which you see on the right-hand side here. And this is provided by Richard Knochemuth at RK Research. Now, it's interesting to consider that the computer is actually becoming part of the analyzer in a way that's similar to how Fourier transform works, where the Fourier transform analysis gives us a high resolving power. In this case, the high resolution demultiplexing gives us the high resolving power. Let's look at a few examples here. Here's a 3 milk oligosaccharides, and we're looking here at these in the standard demultiplexing mode, and you can see the peak on the left-hand side here is a wide peak, and it's not hard to imagine that there are multiple isomers present underneath that peak, unresolved. When we pass it through the preprocessor and the high resolution demultiplexing, then each of those are nicely revealed, each of those 3 isomers. Let's actually look at a comparison now between the standards, individual standards that you can see in these taller 3 plots, and then when combined together into a single sample and run together, which is what you saw before, you see the 3 lower plots here with their labeled isomers. The resolving power on this we're achieving is about 250. So we modeled resolving power of 250. You can easily do that mathematically. And when we go to map that on top, we see very nice agreement. So we're really quite pleased. Let's look at an example of high resolution demultiplexing by examining some work that's been done in Aaron Baker's lab at NC State. One of our students, Karen Butler, has been looking at some asparagine peptides in the lab there that then deamidate and isomerize to both aspartic acid and isoaspartic acid. She's assembled 7 different peptides, examined these in both positive and negative mode. And as you can see from this plot here, these peptide pairs differ in collision cross-section, ranging anywhere from typically about 1 to 3% in collision cross-section. The vertical lines that you see there at about 2.25% represent the limit that they're able to separate directly at a resolving power of 50, typical with drift tube ion mobility. Now, when we apply multiplexing and high resolution demultiplexing, then we're able to achieve a resolving power that allows us to separate down to 1% and in some cases even lower. So let's take a look at one of these pairs. This is a number 2 here, and that had a separation of about just under 1.5%. We can see here in a standard drift tube operation that they're clearly more than they're clearly an isomeric pair here by the profile of the peak, and yet it's still unresolved. When we apply a multiplexed acquisition and then demultiplexed at high resolution, then we can very nicely separate both the aspartic acid and isoaspartic acid isomers of these peptides. One of the things that's very powerful about this technique is that it can be applied for very complex mixtures. And in this case, this is a helicell digest. And we've been able to treat thousands of peptides that have been separated here with resolution enhancement. So instead of having it to be a targeted on one or two analytes during an LCMS separation or switched throughout a separation, we can, in retrospect, be able to treat large numbers. Here's just a quick example, just jumping into that data set. You can see the standard capabilities on the left, and now the high resolution demultiplexing results on the right-hand side. Now, what's nice with this workflow is it can also be married together with a standard data-dependent acquisition workflow. In this case, this sample was first analyzed in standard QTOP mode using data-dependent acquisition, MSMS, taking those MSMS spectra that are generated, doing a database search and identification, loading that library into Skyline, and producing then that Skyline library, which you can see listed on the left-hand side. Now what I've done is I've taken and reanalyzed that. You saw that in the previous slide, using ion mobility separation and processing that data with the preprocessor and the high-resolution demultiplexing. And now you see the same analyte, analyzed now in ion mobility. We have such high selectivity that we can now use just the selectivity of the ion mobility, the mass accuracy, and of course the retention time to give us the uniqueness we want. And because there's no switching back and forth between MS and MSMS, then we're able to capture the full ion current of the precursors at high resolution, high selectivity, and do our quantitation in a way that gives us higher sensitivity than we have been able to achieve previously. Now, the good thing about this technique, the high resolution demultiplexing, is it still has all of the benefits of the drift tube system, in that it has very accurate CCS measurement, very reproducible, and it is standardized off of the interlab study, which allows us to get consistent CCS values from instrument to instrument and lab to lab. And these same techniques and workflows have been used at the McLean lab to generate the collision cross-sectional compendium, which has brought data together from many labs to be able to have a large compendium with extremely good agreement. I believe it's at 0.6 is a typical search space that we can use for agreements. That's percent. Now, to refresh that, once again, we're saying let's focus on high resolution and ion mobility. We have three approaches that we can see as the summary slide. The first we talked about is the trapped ion mobility. And as we increase resolving power, then the percentage of the ion mobility frame that we can use just based on speed limitations decreases. The same is true with the cyclic as we send it around the loop in multiple times. With the SLIM technology, we already start with a very high utilization, the full frame data. And that we achieve a resolving power of about 250. And then in the case of the drift tube ion mobility, we start at about 50, but we can increase that resolving power with high resolution demultiplexing while maintaining full frame data acquisition. Now let's turn the second half of the talk to looking at some work that we've been doing with large molecules. When we look at the collision-induced activation, here is the back end of what we refer to as the desolvation assembly. And you can see this is the capillary that is the exit end of the capillary coming into the mass spectrometer high vacuum. The front end of that, which you don't see, is what's present in the atmospheric pressure ion source. You can see it schematically shown below. Here's that ion transfer capillary. And what we've done is we've added a small cap on the back end, you can see here, that allows us to create a high field potential gradient here between the capillary exit and that cap, so that we can accelerate ions and activate them against the gas that is the nitrogen gas that's emerging from that exit capillary. The ions are then recaptured here in the high pressure funnel, and then they're redirected and trapped in the trapping funnel. We have parallel accumulation, as you saw earlier, so that ions are trapped here while the previous analysis or trap cycle is being performed in the drift tube. We can step that potential over the course of the analysis. In this case, I'm showing a little bit of an extended time, but it can be also shorter. And as we increase that potential, then we're increasing the activation energy that we're going to apply to protein systems. we've been working together with the University of Michigan and the great researchers there, with Brandon, Alexi, and Kiki and their teams, great graduate students and postdocs, and we'll look at some of the work that's resulted. There's a lot that's been published in this. We know the principles. We just mentioned this. Each time increasing the collision voltage in the source ahead of the mobility separation. And as we activate these proteins, they unfold and their various regions start to become exposed. Okay. Now we can plot this. And here you can see this is showing the trapping voltage or the collision voltage that we're applying. In the early days, it was just the trapping voltage that we used. And we can actually compare one result to the other. And these are some difference plots that are shown. Of course, there's been a lot of work that's already been published on this, and I won't refresh all of that here for us today. When we look at this, here's some IgG examples where we've looked across IgG 1, 2, 3, and 4. Those have been published previously. In this case, we're going to turn our attention to a comparison between IgG 1 and looking at some biotherapeutics, in this case used for Crohn's disease. Remicade is the innovator there, and we're going to compare this to the two biosimilars that you see plotted. And you can see how interesting that will be. Do they really have the same structural conformation? As we activate them, are there subtle differences that start to emerge in those intact structures? So let's look at that in more detail. Okay, once again, here we have the innovator and the two biosimilars. And what we're going to do is we're going to now zoom in using this CIU Suite software to be able to look at these inflection points between these static states. So here's one activation energy, a CU, and we call it a 50 because it's the 50% point between these plateaus. Now, we also, in the drift tube systems, can monitor multiple charge states simultaneously. So we're looking at the 25 through 29 charge states, and we're looking then at the CIU, the 50 points for these various charge states, and we're looking at that at both the first inflection here, plotted above, and the second inflection here for the second transition, plotted in the below. And you can see in this case, for example, in the 27 charge state, look at the differences between these various, between the initiator, the innovator, and the biosimilars, okay? Particularly between the renflexes. You can see that right there. So by actually being able to profile across charge states and combining all of this information together, we can have a very good p-value for being able to distinguish between innovators and biosimilars. Now let's add some additional information to the story. Let's look at adding collision electron capture dissociation to the collision-induced unfolding. This work you're going to hear about more today from Joe Beckman. So this is just a one slider where we've been able to insert an ECD cell on front of the collision cell. The collision cell has been shortened just slightly to accommodate that ECD cell. Okay. Now, with that, we're going to look at producing ECD fragments, okay, under two different activation states in the protein. One here with low collision activation, and one here where the protein is more unfolded, okay? And as we do that, we can get ECD spectra. We can get those ECD spectra at low energies, at high energies. We can also do CID experiments still. And here we're showing how we can combine these together. So here's 100-volt activation. Here's 400-volt activation, you can see in the red. And combined, we're getting a lot more information than we were. Now, let's look at human serum albumin. Same story here. We've got that activation. Okay, here's the HSA. Here we are largely intact. Here's now performing ECD. And as I mentioned, we can also do CID studies as well. So let's look at this again. Here's at 150 volts of activation in the source. Not much unfolding at that point. Okay, that's still the compact form. Now at 250, we get a very different ECD spectrum. Notice all the information that we're able to achieve there, okay? And what that allows us to do is start to make an association of the various domains where those fragment ions are starting to be produced either by ECD or by collision-induced association in those subunits of the protein. There are other activities now for the very end of our talk. I mentioned that we'll spend just a second on imaging. You're going to have more of that today from Vladimir, who's the last talk of the day. But the first one to highlight is some work that we're doing by coupling IR Maldesi to our 6560. This is ion mobility. As you can imagine, in the short drift times that we have, we're able to couple this very nicely to laser pulse rates, and the circuitry that you see on the right shows how those have been enacted together. We're also able to work with AP Baldi imaging, and as I mentioned, that's what you'll hear more about today. Okay, so lastly, I would like to thank you for your attention and would invite any questions that you might have.
Thank you so much, Dr. Fjeldsted, for that informative presentation. We've already received some great questions, so we're going to begin the Q&A portion of our presentation, and I want to encourage our audience to go ahead and ask some questions. You can go right to that left side to the Ask a Question box and click Send. So let's take a look at the questions that are already coming in. Our first question is, when will the SLIM technology be commercially available?
Yes, it's a great question. We're currently working together, as I mentioned, with Mobile Ion. They have several beta systems that are already in deployment in key labs across the US, and great results are coming back from those. The actual launch of the product is due for the ASMS timeframe this coming year in 2021. So we're quite excited about that.
Thank you so much. And is there a requirement of specific signal strength required for doing the multiplexing? And this is a two-part question, John. The problem we are facing, the audience member says, the problem we are facing during the multiplexing is that it is not effective for low intensity signals. The traditional step field technique is more effective at times where the signal intensity is very low. So they're wondering, is there a requirement for that specific signal strength?
Actually, no, the signal strength can go very, very low. There are some cases where somebody loses the sequence in the pseudorandom sequence and then it doesn't decode properly. So that's a defect that I have seen. And I believe that the question and the source where it's coming from, I've looked at that data and that answers that question quite well. No, the signal levels can be very low, and it does help it in sensitivity in that regard. For the high resolution demultiplexing, because that involves a deconvolution step, then yes, ion statistics does play a role in that. Mm-hmm.
Thank you so much. And do you see a sensitivity enhancement for the ion mobility enable applications?
Yes, absolutely. If you look at the fundamental duty cycle, then it can be as high as 50% with multiplexing. So that's why I say it really is a sensitivity enhancement there. And yet we get an 8-fold factor measurement cycle. The opportunity the ion mobility presents is because you have a second degree of separation before ion mass measurement, then interferences can often be removed from that analysis. And so that gives you a substantial increase in signal to noise. And this is particularly predominant, can be seen very nicely, for example, in proteomic applications as well.
Thank you so much. Dr. Fjeldsted, how effective is the SLIM technology for separating stereoisomers in essential oils? What is the drift gas used for in the chiral molecules?
Yeah, trying to do chiral separations, that is really a push. That's a challenge. That's getting down require resolving power that's higher than what we're able to do in drift time ion mobility in most cases. I think this would be a great opportunity to start posing those types of problems for the SLIM technology. SLIM technology has incredible resolving power capabilities, and that'll be exciting work to see in the future.
Dr. Fjeldsted, thank you again for your presentation today. Would you like to provide any closing remarks for our audience? And I do want to remind them, before you say anything, as a reminder to all of them, questions we didn't have time for today and those submitted during the on-demand period will be addressed via the email you provided at the time of registration. Go ahead and provide some closing remarks before we go today.
Yeah, there's one question I see coming here at the end. You know, great dynamic range enhancements that we're seeing from these technologies. So factors of between 4 and 10. I'd like to just say that it's an exciting time for trying to solve the unsolved with ion mobility, being able to pull out isomeric and conformeric information about small and large molecules is a new opportunity. It's like when we went from low resolution mass spectrometry with quadruples to high resolution mass applications as well. The world started to unfold for us, and I think we're going to see that over the coming years. Thank you very much.
And thank you again, Dr. Fjeldsted, and thanks for everyone who participated. We encourage you to check out the exhibit hall and the rest of the Agilent event. Take care, stay safe, and stay healthy. Bye-bye now.
Mm-hmm.